Neptune has 14 moons. One of the moons, Galatea, has an orbital radius of 6.195 times 10 to the 7th meters and an orbital period of 0.4287 days. Notice we've relaxed our restriction on numbers only having 3 significant digits. What is the mass of Neptune? Another moon, Despina, has an orbital radius of 5.253 times 10 to the 7th meters. What is its orbital period? Yet another moon, Hippocamp, has an orbital period of 0.936 days. What is the radius of its orbit? And then Neptune rotates once every 16 hours and 6 minutes, or 0.6708 days. At what height above Neptune's surface? It's hard when you're doing gravity not to say Newton, isn't it? So you want the height above the surface. Will a satellite maintain a constant position? What is the mass of Neptune? Here's our statement right here. Kepler's third law, which is the title of the problem, makes it handy. It has 3 variables: the period, the radius, and the mass. So you have period here, radius of the orbit, and the mass of the object that you're orbiting. Big G is the universal gravitational constant, and we're familiar with pi, hopefully. And here's a key right here. This is a very common mistake. The mass there, that's the mass of the object being orbited. So if you have a moon going around Neptune, big M is the mass of Neptune. So please don't make that mistake. It's not the mass of the orbiting object, it's the thing it's going around. So let me just erase over here on Kepler's third law. And what are we trying to solve for? The mass. That's down here. So we have to rearrange this equation. So first, let's cross multiply. And that means gm times t squared, and then 4 pi squared times r cubed. And let's see if that's what we get. Yep. So hopefully you're familiar with that from algebra at this point in your education. If not, well, you just learned it. That's legal. You can cross multiply like that. We want to solve for m, so we have to isolate m. And we're going to do that in one step. We'll divide both sides by gt squared right here. That will cancel out the g and the t squared here, and we now have our equation for mass. Most of the problem is done. And now, sorry about this calculation. This is where a calculator comes in very handy. You have to plug all these numbers in. So I do recommend doing this a couple times just to check your answers. And then you wind up with 1.03 times 10 to the 26th kilograms. Now, what didn't I mention that I should have earlier? We talked about days here. That's not an SI unit. We can't use that in the equation. We have to use seconds. You have to use meters, you have to use kilograms, and you have to use seconds. So down here shows the conversion. We have 0.4287 days, and what do you have? You have 24 hours in a day. So this day, which is in the denominator, will cancel out with this day, which is in the numerator. Well, we're still not good. We need to get to seconds. So how many seconds are in an hour? You may never thought about that. You know that there's 60 seconds in a minute and 60 minutes in an hour. So you multiply 60 times 60 and you get 3,600 seconds in an hour. So we've now crossed this out. That's denominator, numerator. And the only variable we're left with is seconds, which is where we were going. Carry out the math and you get that 3.70 times 10 to the 4th seconds. And let me just erase because I want to highlight where that is. And switch to the pen. Here's where the time is. Now be very careful with the exponents here. There's a lot going on. You have a cube over here for the radius of the orbit. That's from the center of Neptune to the moon Galatea. You have a square here for the time, for the period. Make sure you catch that. Now we're given the orbital radius. All right, that's from the center of Neptune to Despina's center. And there's our radius, and we want to find the period. Well, there's a number of ways we can do it. We can just go ahead and look at this guy here and plug in the radius, plug in the mass of Neptune, plug in the gravitational constant, and grind it out. But there's a more elegant way of doing that. And that's the way we're going to choose, because I just told you how to just brute force it, which isn't very cool. We're going to start with this. That's Kepler's third law. These moons, Galatea and Despina, orbit the same planet. That's Neptune. So look at the right side of Kepler's third law. This is constant for everybody orbiting Neptune. right? 4 is a constant, 5 is a constant, big G is the universal gravitational constant, and M is the mass of Neptune. So we're going to do something fairly clever here. On the left side of this equation, we have the period squared of Galatea and its orbital radius cubed. That has to equal the square of the period of Despina and the cube of Despina's orbital radius. We will then solve, what do we need here? We know all the things about Galatea. We know the radius of the orbit of Despina. We just need to find the period. So we need to isolate T sub d, or the period of Despina. So what did we do here? We did a partial cross multiply. We multiplied both sides by r sub d cubed, this term here. So we now have Td squared all by itself, but we want Td, the period. So we take the square root of both sides. And we actually did a couple steps to the next point. Inside the radical here, we have the square of the period of Galatea. Well, if you have a square underneath the square root, you can just bring that value outside, which is what we did. This way we don't have to square it first and then take the square root. We're just wasting time. Now we plug in our numbers. And the nice thing about this one, on the previous slide we had to convert days to seconds because we should always work in the units of seconds, meters, and kilograms. But this time we've got a ratio. And the days will just match each other, okay? Because right here, you've got radius cubed over radius cubed. The meter cubed will just cancel out inside. And if this is in days, well, our answer here will be in days. So we saved some unit conversion here, and we saved doing a bunch of calculations with the mass of Neptune. So this is pretty elegant. Put the numbers in, and then go ahead, cube both of these, take the square root, and we get 0.335 days. Another moon, Hippocamp, has an orbital period. Find the radius of its orbit. Again, we're going to use this ratio here because the right side of Kepler's third law is the same for both Hippocamp and Galatea. So we set them equal to each other. And now we're going to cross multiply, right, which is legal. So we have Tg squared times RH cubed. Got to keep track of the exponents here. It gets pretty tricky. And then the right side will be Th squared Rg cubed. We're solving for the radius of the orbit of Hippocamp. So we isolate that by dividing by Tg squared on both sides. And then we take the cube root of each one. Cube root, this is tricky. So if I take the cube root of the cube of Galatea's radius, that just comes outside. So that's just r sub g. Then I have the radical, and it's kind of written like this. This 3 here means it's not a square root anymore, it's a cube root. So I hope you can do that on your calculator. And one way of doing it is you plug in the number underneath the radical, you hit that caret form, and then you type in 1 divided by 3 for 1/3, because that's what a cube root is. Or you could just type in 0.3333, and that's close enough. And if you need more help, please check with your math teacher. So I put in the numbers, and once again, I'm just going to use days. I don't have to convert it to seconds, because why? They cancel out. So I can save some calculations there, and I get an orbital radius of 1.04 times 10 to the 8th meters. Now we have a problem where we would like to put a satellite maintaining a constant position in orbit around Neptune's surface. We do that on Earth all the time. For example, GPS satellites, if we're in southeast United States and we want to keep track of where we are, we need the satellite above us always to stay in the same position, so it can always tell us where we are. So here we're going to do it on Neptune. We're going to use Kepler's third law here, but not the whole law. We're going to take advantage that T squared over R cubed is the same for everything going around Neptune, whether it's a satellite, rocket ship, or a moon. So we're going to have the variables here, T sub s and R sub s. That applies to the satellite. Here's the information we have with Galatea. We'd like to solve for the orbital radius, which is R sub s, so we cross multiply like we've been doing. This is a handy trick for these type of problems. We get this. We then divide through by Tg squared to isolate Rs cubed. Take the cube root of both sides. And when you take the cube root of a cube, you just get that number back, or letter. So we put RG out in front. Here's our cube root over here, right? I'll just remind you how that goes. There's a 3 here on the radical sign. And what period do we use for the period of the satellite? They didn't tell us. Well, they did. They want the satellite to maintain a constant position, so it has to have the exact same period as Neptune rotating. So as Neptune rotates, the satellite rotates in sync with it, so it always stays in the same position. So we have our equation here, and what do we have here? 0.6708. That's the orbital period of Neptune, and also the satellite now. So we put that in there. Here's Galatea. Carry out the numbers, and we get 8.35 times 10 to the 7th meters above the center of Neptune. But look at the question. What did they ask for? The height above Neptune's surface. That's kind of tricky, okay? Kepler's law works between the centers of your masses or planets, so we're not quite done yet. So how can we finish the problem? This is the orbital radius of our communication satellite. That's from the center of Neptune. So what do we have to do? We have to find out how far it is above the surface. So here's Neptune. Here's our satellite. Not sure why I drew it like that. We were given that we found this distance, okay, that's R sub s. But we want this distance. Okay, so what do we have to do? We have to take R sub s and we have to subtract away. What are we subtracting away? We have to subtract away the radius of Neptune, okay? So when you subtract that away, you get this, the height above the surface. So we have the height above the surface is the orbital radius from Kepler's law minus the radius of Neptune. So that's 8.35 times 10 to the 7th minus 2.43 times 10 to the 7th. And here's our final answer, 5.92 times 10 to the 7th meter above the surface.